Greetings and welcome, friends. Mr. Waddy here, and my freshest batch of geometricians, soon-to-be geometricians. They'll get there. Don't worry, internet friends. Today we're talking about section 1.2, measuring and constructing segments, and we're talking about this cool idea right now, the ruler postulate. And it says, in geometry, a rule that is accepted without proof is called a postulate or an axiom. Now, throughout geometry, because geometry, like other branches of mathematics, math is discovered, all right? It's innate within our universe. And we need, like, the building blocks, we need the atoms of geometry, and our smallest starting point in geometry are these things called postulates, things that we feel are obvious building blocks that we don't need to prove them to you to accept that they're true. And then using these postulates or axioms, we will then start to combine them and apply them in different things that we observe. And we'll be able to discover additional facts called theorems, all right? And we'll be able to prove them very logically, all right? So a rule that can be proved is called a theorem, as you will see later. Ooh, foreshadowing. How foreboding. Oh, man, you guys are going to hate theorems and then love theorems. I might have lied about the last part. So anyways, as you will see later, Postulate 1.1 shows how to find the distance between 2 points on a line. So as far as measuring things with like a ruler, we've got this ruler postulate, which says the points on a line can be matched 1-to-1 with the real numbers. Okay, so like think about the number line. And the real number that corresponds to a point is called the coordinate of the point. And in terms of 2 dimensions, you guys have seen ordered pairs, x, comma, y, right? There's actually also ideas of ordered triples for 3-dimensional space. You can also go beyond 3 dimensions in linear algebra. That's weird. And this is, yeah, so ordered triple. Any component for these are called, I believe that's an ordinate. But also there's other names for just the x and y. It's weird. Ordinate and abscissa? So, I don't know. Anyways, the real number that corresponds to a point is called the coordinate. So the point would be a, but the coordinate might be like -2 or 7, right? So I'm assigning a number to that location. So this is referring to the figure, right? The picture point, right? And this would be referring to a number describing the location of the point, right? So you are a person and you are not simply the location in which you exist, right? But you as a person, your location could be described, I don't know, with like GPS coordinates or something like that. The distance between points A and B, written as AB. Now, I want to point this out. AB is referring to the line segment. So this is like the picture, where AB is going to be a number representing the length of that picture. Okay, so one of these is describing the image, the other is describing, right, the distance from one point to the other. All right, so in terms of notation, it's subtle, right? That is now a picture. This is a number. Picture, number. Picture, number. Bam. And the distance is the absolute value. Could someone describe for me what absolute value is? What is that? All right, so it's the distance a point is from 0. And then fact about absolute value, he said, was that it can't be a negative number. Agua. So, yes, true. And distance, we are going to describe distance as always being positive. In fact, the Greeks' view of mathematics was largely through kind of the window of geometry. And when they talked about distance and things, they always thought about things as being positive. Because, yeah, they were thinking about it geometrically. And when I talk about it, how far am I from my house right now, I wouldn't say like negative 23 miles. I would say 23 miles, right? We measure positively. and it's the absolute value of the difference, so that's subtract, of the coordinates of A and B. All right, so AB, that's not the segment, that's the distance, it's a number, is equal to the absolute value of the difference of those numbers, and distance will always be positive. So let's see what I can do here. All right, let's apply the ruler postulate in example 1, and I might, let's see. Now here's a problem. Like, how do I get a ruler into my digital space? That's a little bit weird. I'll show you this in real life as well. We'll do it. Don't worry. I'll show you guys my hands today. Although my face has been shown on the internet before. So if this is a ruler, I just want to point out, like, typically you would like line up your ruler with one of the points at 0. Right, that's typically what you would do. You could even like, whoa, flip it around, and let's see how well I can do that. Maybe I can't. I can't, apparently. There we go. Right, you could do that. And we typically would line it up with one of the points at 0. Right, and that's the easiest way to do that. It looks like 3.9. But I want to point out, we could actually have the coordinates of one of the points not be at 0. So this might have a coordinate of 1. This might have a coordinate of 4.9. And ST is going to have a distance of the absolute value of 4.9 minus 1, which is 3.9. Same distance. Also, it could have equaled the absolute value of 1 minus 4.9, which would have been the absolute value of negative 3.9, and absolute value always making that positive is so. So I want to point out, like, the ruler postulate, yeah, always line it up to be 0, but it does apply when it is not that particular, right, when the coordinate doesn't have to start at 0. Let's see, here we go. Ooh, look at it. Ooh, I should be like a hand model or something. Here we go. Looks like I need to rep. All right, so ruler postulate, just because you guys have a physical piece of paper and I don't know if it's actually 3.9 centimeters, I should actually line this up at some point. Now, it looks like mine's more like 5 centimeters, or maybe I'd call that 4.9. I'll call it 4.9. So your physical space, yeah, actually, yeah, if you want to, yeah, Liam, that'd be great. Go grab some of these little guys. Maybe distribute some. There's multiple colors. Ooh, so this is like a cool multi-tool. Like if Les Stroud, when he goes out into the wilderness, he brings one of these every time. Les Stroud, Survivor Man? No, that's probably an old reference these days. But yeah, Bear Grylls. I'm a fan of Bear Grylls. Les Stroud, I feel, is a little bit more authentic. Also, side note, it might be hard to find this on the internet, but my name's Brian Waddy, and some people call me Captain Wilderness. What? Wow, I'll have to show you that someday. Anyways, but here we go. We've got yeah, you measure the distance like so, and this is a multi-tool. We'll use it in a few different ways. And I just want to point out that no matter what coordinate I start at, right, even if I have like 2.4 and 7.2, right, I could subtract those and still get the same distance. All right, so there you go. You got the idea. You get it. You get it. And actually, oh, this is a distance. Once I was attributing this not just to a number line, but units of measure, I should actually label these with those units, right? Because, yeah, I could have been talking about 3.9 astronomical units, right? The distance of the Earth to the sun. Or 3.9, I don't know, is like the width of the universe a thing? Sure. Diameter of the universes I could have been talking about. Or Planck lengths, like we were saying earlier. I could have been measuring any of those, but we'll apply this number specifically to, wow, man, cold medicine. Centimeters, which I do want to point out, like the idea of centimeters or fathoms or cubits or inches or yards, knots, right? All of those distances are somewhat arbitrary, not completely. I mean, scientifically, they've related some of these things to our physical universe a little bit more than just like the length of someone's forearm. But yeah, they're somewhat arbitrary or specific to where we live in the universe or what universe we live in. I personally don't believe in a multiverse theory, but whatever. Congruent segments. Chop, chop. Line segments that have the same length. So this would be like their measure, right? So I would say equal numbers, right? Number equals number are called congruent segments. All right, line segments. So this is the picture or the diagram, right? The actual image that I'm talking about, the object, is congruent to another object if its length is equal to the other object's length. So you can say that the length of segment AB is equal to the length of segment CD. Equality applies to numbers. Okay? Congruence applies to objects. All right? And this congruent symbol is like an equal sign that's wearing a toupee because it's got like a midlife crisis. It's like, man, I don't look as young as I used to, and I just really, I'm trying hard. So I got this little swoop going. You're looking good, equal sign. You got to get yourself out there. But that's not an equal sign. That's a congruent symbol. Yeah, you're good. Go. So the symbol congruent is congruent to. And so the lengths are equal, but the segments are congruent. That means the objects are the same in terms of shape and size and angle, if that existed for this, but they don't because these are line segments. So we could label these congruent like this. Notice I'm describing the object. Here I'm describing numbers. So numbers are equal, objects are congruent. Okay, so those objects will actually apply this congruent symbol to describe segments and angles and triangles and polygons. Technically, you could apply them to polyhedron, right? Congruence is describing objects, all right? Subtle difference, really subtle. Also, in a picture, you can label congruence with this little tick mark. Any two segments that I label with a single tick mark, hash mark, little slash, right, is saying that this segment is congruent to that segment. So in, say, a poorly drawn rectangle, here we go, I could say that this side is congruent to that side. But what if I want to say this top side is congruent to this one? I wouldn't want to label it this way because that would be saying all four of these are congruent to each other. So mathematicians actually will use then a double tick mark and say anything with the double tick mark is congruent to anything else with the double tick mark. All right, and then likewise, like if I had some arbitrary third length, right, I could do triple tick marks. These don't ever get to be like tally marks where like you don't do that, but there you go. So there's a way to describe congruence between those. So congruence is when they are equal in measure, the objects are congruent. Congruent things have the same size and shape, right, is what's going on there. So here's example 2. All right, plot. Oh, wow. Let's see. Maybe we haven't plotted points in a while. Let's plot J at -3, 4. So here's a two-dimensional coordinate plane starting at the origin where the y-axis and x-axis intersect. The positive x-axis is over here. The positive y-axis is going up. And -3, 4, these coordinates are in the form x, y, right? Alphabetic order most of the time, unless you were describing like time and money or something like that. Then you might have the t goes first. Often our x-axis is corresponding to time. But -3, 4 would mean to, starting at the origin, move left 3 and up 4, plot that point. And we can, hey, let's throw a J on it. Here's the point, 2, 4, over 2, up 4. Plot that point. There's K. Okay. L is at 1, over 1, up 3. So here's L. And M is at 1, -2, over 1, down 2. M. And then it says, determine whether JK and LM are congruent. All right, so they left the space of just having points. They then made these into segments. So this is segment JK, and I guess I'll label this one blue. Ooh, classy. Man, I love my colors. Muchos calor. I don't think that's how you say color in Spanish, is it? It is? What? How do you say? Oh, I was thinking like caliente is hot. I was worried I was like just using a pseudo Spanish. Sí, excelente. So let's see. Now, if I want to find the distance from J to K, notice these are kind of horizontally oriented to one another. This is -3 over, and this is 2 over. So if I want to find JK, the distance, I could actually just do the absolute value of their difference. Because these are conveniently horizontal. If this was like diagonal, that's a no-go. You're going to have to use a different distance formula, friend. 2 minus a -3 is the same as 2 plus 3. Yeah, I guess I'll do a little work vertically here. Abs 5, I get 5 is the length of JK, the distance from J to K. All right, equal signs apply to numbers, right? And then if I want to find the length of L and M, these are vertically oriented to one another, so I'm going to actually use their y coordinates, so 3 and -2, and so I'll have LM, the distance, is equal to the absolute value of the difference. Actually, let me do it intentionally the other way, -2 minus 3. And I'd have abs val -5 is equal to +5, is LM. Now, if JK is 5 and LM is 5, do you think I could say that JK is equal to LM? Using the transitive property, if they're both equal to the same thing, they're equal to each other, and therefore JK, the segment, is congruent to LM, the segment. These statements say very different things, although they look very similar to each other. I think you would agree, right? JK equals LM, and JK is congruent. The segment is congruent to LM. And since those are congruent, I could even put my little right, little slash marks in those if I want. Let's see. I feel like I gotta pick up the pace, Mr. Watty. Oh yeah. Here we go. All right. I don't know. I've been too excited talking about this stuff, and my voice sounds so great, and now it's going to be preserved on the internet for generations as long as Google servers last forever, and then my great-great-great-great-great-great-grandchildren will be able to learn geometry from me. Wow. It's pretty awesome. Segment addition postulate. This means believe it. I don't care. You believe it because it's true. I don't need to explain myself. This is a postulate. And it says when 3 points are collinear, you can say that one point is between the other two. That makes sense, right? This one's like between A and C. Yeah, I believe that. And segment addition postulate, which, by the way, these addition postulates will also apply to angles and areas and volumes. Yeah, it's going to be great. And the segment addition postulate, ready? This is going to blow your mind. You're going to believe it because it's true, and I'm not going to prove it to you. It says if... All right, I'm going to drink some water. Go. So, if B is between A and C, then AB plus BC is equal to AC. The big length is equal to the sum of the two smaller non-overlapping parts. Yeah? Right? That just makes sense? Yeah, you just believe this, right? And then it's also true in the other order. Notice this if-then logic got swapped. If-then. So if B is between those, then this is true. And if this is true, then B is between those. Those say different things. Chapter 2 will practice some of that logic. But yeah, segment addition postulate. You guys, it's going to make the most sense. Don't worry. We're good. All right, example 3. Find DF. So I'm going to say that DF notice I'm referring to a number, not a segment, is equal. So since these are numbers, I can use equality. Is going to equal 23 plus 35. DF is going to equal, looks like 58, maybe. Wow, my voice sounds so weird. I'm not used to it. But you guys, maybe this is all you know that I sound like, because we're so new as friends. Wow. So weird. And slightly more interesting, using a little bit of algebra. Uh-oh, dear guys. Oh my goodness. So FH would have equaled FG plus GH. Do you agree? Right? The big length is equal to the sum of the two smaller lengths. And now if I do some substituting, FH is 36. FG is 21. GH I can refer to as GH. Or you could have made up some other, like, little lowercase variable x or something like that if you're a fan. And how do I solve for GH? Oh man, you guys are loving the algebra. We're in geometry, but we be doing some algebra right now. This is pretty great. 36 minus 21, that feels like 15. I'm calling it 15. I love it. I love it. Yeah. Let's see. Last example, example 4. So yeah, notice, you guys might notice on your notes that you've got additional problems. They're from the monitoring progress sections in your book. If you wanted to practice more of these types at any time, you could choose any of those problems and they would be available to you. But I'm just going to do some examples today. Sometimes I do the monitoring progress as well if I feel we need the extra rehearsal. The cities shown on the map lie approximately in a straight line. Find the distance from Tulsa, Oklahoma to St. Louis, Missouri. Okay. I'm gonna say LS is gonna equal the LT plus the TS. Right? That feels true. The entire distance is 738. And 377 is LT. And these are measured in miles. Oh my. Plus TS. And let's solve for this TS. Subtract 377 from both sides using the subtraction property of equality. And I'm gonna flip it as well using the symmetric property of equality. And I end up cheating and looking at my book. 361 is what that's equal to. So the distance is 361 miles. So, thanks for watching, internet friends. I'll see you in Tulsa.